Let p be a prime number. Find all integers k, such that root of k squared minus p times k is a positive integer. Clearly, root of k squared minus p times k is a positive integer, implies that k squared minus p times k is a positive square. How to solve this problem? It seems to be not straightforward. We are given that p is a prime number. The only even prime number is 2. So we first consider if p equals 2. In which case, k squared minus p times k becomes k squared minus 2k, which can be written as k minus 1 all squared minus 1. Assume k minus 1 all squared minus 1 is a positive square. We let k minus 1 all squared minus 1 equal n squared, where n is a positive integer. Rearrange the equation. We have k minus 1 all squared minus n squared equals 1. K minus 1 all squared minus n squared can be written as k minus 1 plus n times k minus 1 minus n. So either k minus 1 plus n equals 1, and k minus 1 minus n equals 1. Or k minus 1 plus n equals negative 1, and k minus 1 minus n equals negative 1. In either case, n equals 0. This is a contradiction to that n is a positive integer. So if p equals 2, there are no solutions. So prime number p must be odd. Case 2, if p divides k. Then we let k equal mp, where m is an integer. But m does not equal 0, or 1. Because, if m equals 0, then k equals 0. So k squared minus pk equals 0, so it cannot be a positive square. If m equals 1, then k equals p. So k squared minus pk equals 0, so again, it cannot be a positive square. When k equals mp, k squared minus pk equals p squared times m minus 1. Assume p squared times m minus 1 is a positive square. We let p squared times m minus 1 equals n squared, where n is a positive integer. As m and m minus 1 are co-prime. That is, the greatest common divisor of m and m minus 1 is 1. So m and m minus 1 cannot both be squares, or negative squares. Note that the only consecutive squares are 0 and 1. But, as m does not equal 1, so m and m minus 1 cannot be 1 and 0. Therefore, m and m minus 1 cannot both be squares, or negative squares. This implies that the equation p squared times m minus 1 equals n squared has no solutions. So p cannot divide k. Case 3 is the last case we need to consider. P does not divide k. Then k and p are co-prime. We know that k squared minus pk can be written as k times k minus p. As k and p are co-prime, so k and k minus p are also co-prime. This implies that k squared minus pk is a positive square, if and only if k and k minus p both are squares, or both are negative squares. When k and k minus p both are positive squares, we let k equal m squared, k minus p equal n squared, where m and n are positive integers. Then we have p equals m squared minus n squared. M squared minus n squared can be written as m minus n times m plus n. So we can now write m minus n times m plus n equals p. As p is a prime number, and m plus n is greater than m minus n. So we have m plus n equals p, and m minus n equals 1. Add these two equations, we have 2m equals p plus 1. So m equals p plus 1 over 2. As k equals m squared. So k equals p plus 1 all squared over 4. When k and k minus p both are negative squares, we let k equal negative m squared, k minus p equal negative n squared, where m and n are positive integers. Then we have p equals n squared minus m squared. N squared minus m squared can be written as n minus m times n plus m. So we can now write n minus m times n plus m equals p. As p is a prime number, and n plus m is greater than n minus m. So we have n plus m equals p, and n minus m equals 1. Subtract the second equation from the first equation, we have 2m equals p minus 1. So m equals p minus 1 over 2. As k equals negative m squared. So k equals negative p minus 1 all squared over 4. It is easy to check that, when k equals p plus 1 all squared over 4. K squared minus pk equals p plus 1 all squared over 4, all squared, minus p times p plus 1 all squared over 4. P plus 1 all squared over 4, all squared, is equal to p plus 1 all to the power of 4, over 16. Now the two terms have a common factor, p plus 1 all squared over 16. So they can be factorized and written as p plus 1 all squared over 16, times p plus 1 all squared, minus 4p. P plus 1 all squared, minus 4p, equals p minus 1 all squared. So we can now write, equals p plus 1 all squared, times p minus 1 all squared, over 16. Which can be written as, p squared minus 1 over 4 all squared. Which is greater than 0. So k squared, minus pk, is indeed a positive square. Similarly, when k equals negative p minus 1 all squared over 4, k squared, minus pk, equals negative p minus 1 all squared over 4, all squared, plus p times p minus 1 all squared over 4. Negative p minus 1 all squared over 4, all squared, is equal to p minus 1 all to the power of 4, over 16. Now the two terms have a common factor, p minus 1 all squared over 16. So they can be factorized and written as p minus 1 all squared over 16, times p minus 1 all squared, plus 4p. P minus 1 all squared, plus 4p, equals p plus 1 all squared. So we can now write, equals p minus 1 all squared, times p plus 1 all squared, over 16. Which can be written as, p squared minus 1 over 4 all squared. Which is greater than 0. So k squared, minus pk, is indeed a positive square. We can work out the values of k, for a specific prime number p. For example, for p equals 3, the positive value of k, equals 3 plus 1 all squared, over 4. Which is 4 squared over 4. Which is just equal to 4. The negative value of k equals, negative 3 minus 1 all squared, over 4. Which is negative 2 squared over 4. Which is just equal to negative 1. For p equals 7, the positive value of k, equals 7 plus 1 all squared, over 4. Which is 8 squared over 4. Which is just equal to 16. The negative value of k, equals negative 7 minus 1 all squared, over 4. Which is negative 6 squared over 4. Which is just equal to negative 9. Examples of k are 4, negative 1, when p equals 3, and 16, negative 9, when p equals 7.